Okay, here we go. Let's look at the the practice quiz 1.3, and we're going to be talking about question number 55. And so I just started explaining this to the class, and they're going to have to listen to this all over again. Poor class. All right, here we go. And let's get that shade up. Come on. Here. Okay, what we started out with is I was trying to show that, and hold on just a minute. Okay, so here we go. Let's look at AMUs. AMUs are atomic mass units, and one atomic mass, the total mass in AMUs convert to total mass with 6.02 times 10 to the 23rd atoms. That's 1 mole of atoms, and we'll talk about moles later. But if we take our AMUs and multiply by this number, we get the mass. So we can either read the periodic chart as AMUs, or we can read it as mass. Does that make sense? Okay, and mass are in grams, and grams is for almost any of the atoms up there, especially as you go past fluorine. You know, you've got stuff that you can see. Okay, like fluorine is how many grams? Fluorine is about 18, 19 grams. Okay, so you got 19 grams. You can actually see and feel that. Yeah.
So for number 45, is the answer grams or AMU?
In number 45?
Yeah.
Okay, 45 on this same sheet. Going back. What is the units in metric mass? What units is the atomic mass reported in? Grams. Yeah. Yeah. Atomic mass is reported in grams. And the mass, the atomic mass that you see on the chart could also be considered AMUs. But normally we use that as grams because that's what we use in all of our calculations as we go through the year. Okay. Now, where did this 55 come from? This was given to us. And if you look at question number 55, right below the question number is another 55. It happens to be identical to the question number. So that led to some confusion. So there's our 55. And let's get this curved a little more, or bent a little more, or off to one side. So the 55 is the mass number, and the 25 is the atomic number. And what I decided to do when I did this calculation was to take, since the question had 7 atoms, I started out with the 7, and then I multiplied that by the total grams that we would have if we had 55 AMUs. Because the conversion of AMU to grams was 1.673 times 10 to the minus 24 for each AMU. So 55 AMUs, the number of the mass for manganese. Okay, the 55 is multiplied by this number to get the grams. If we had only 1, it would be 1.673. If we had 2, it would be double that. But we have 55. Now let's reveal this down here. And what I was trying to show here is that 1 atom is what we have here. That will be the total mass for 1 atom. Rather than multiply that out and then start another line, I decided to do the whole thing in one play, and so I multiplied the 7 times the 55 times the 1.673 times 10 to the minus 24. So looking at just these two numbers, as we multiplied these two guys together and then multiplied them by this, we come up with 644. And that's still times 10 to the minus 24. And if you do that on your calculator, you'll probably get it wrong. I've seen people that really know how to do the powers of 10, and when they get on a test, they just mess it up. So I recommend using my method, which is keeping these two guys separate. Use your calculator for this number, and then mess with the scientific notation when you're done. Now, this guy sends the decimal, which is actually right here. It's not written, but it's right here, isn't it?
Yeah.
Okay, so this 10 to the minus 24 sends us 24 over this way, right? Okay? Since we go to the left, and we have to move our decimal from here to here to make it scientific notation. So we can't change the size of the number, so we have to modify that minus 24, and because we've already gone from here to here, which is 2, we have to subtract that from the 22, because I went the same direction that this negative power up here was telling me to go. Negative powers always move decimals to the left. Positive powers will move it the other direction. But when it's negative powers and we move the same direction, see where we put the decimal? Okay, that makes this one have to be 2 less. Because we've got to go 22 from this point now, rather than 24 from this point. And we'll land in the same place, right? Let's pretend that this is 2 and 4. Okay? For 4, we would go to here, wouldn't we? From here, we go, 1, 2, 3, and then a point, 0, 6, 4, 4, right? 4, 10 to the minus 4 would take us from here, 1, 2, 3, and a 0. Now, when we start from here, and we go 2, it would be 1 and a 0. And it would be 0.06. So we know we've got the same number. Very, very important. You can't change the number. And so this guy is our final answer in scientific notation. And that's 7 atoms of manganese. And how much it would weigh? Not very much, huh? You can't see that. You'll never be able to see that. It's too small.
Never say never.
With the right kind of microscope. With the naked eye, you'll never see it. Trust me, that's not going to happen. Now, maybe in the next life, if we have perfect eyes and we can, there's some way to make our eyes into magnifiers. I don't know, but there's probably something will happen then. Anyway, now this dude is the same kind of question that we had on page 104 of the textbook, number 17, and I've done a video on that. Okay, and that's on my website, and you can look that up. In this problem, we are told 2 isotopes of element X. We don't know what element X is, but we're going to figure it out real quick. Okay? So what we do here is we start out, and let me see if I can get my little black cover thing. Here we go. Let's get this guy down. And take a look at this. There we go. Kind of helps to cover up this other stuff so that we don't get lost in the numbers. All right, so we were given this X. The isotope is 79, and the 79 is the number that we see at the top of the chemical symbol, right? Okay, so the actual AMUs for 79 is 78.918 AMUs. And can you see how that becomes 79? We round this. So the 9 makes the 8 into a 9. And for the element X isotope 81, we take this number, and again there's a 9 to the right of the decimal, so that becomes 81. Okay? Now, we are given these abundances. And I didn't put this percent here, so we'll put that in now. So we multiply, when we multiply these guys by a percent, what do we have to do to the decimal? Huh? We have to move our decimal to the left.
Oh, yeah,
Yeah? Because when you make a number into a decimal, you have to multiply by 100, and that makes it a percentage, or a decimal into a percentage. Okay. When you have a decimal number or any number and you multiply by 100, it makes it a percentage. So 100 is supposed to be the whole amount, and any percentage less than 100 will be a part of the whole. So as we go over here, we multiply the 79.918 times the 50.69, we come out with the number 40. And as we do the 80.917, multiply that by the 49.31%, we get 39.9. And so what is the average mass for manganese? 79.9. Actually, let's look and see if we can figure out how we get that. Open up the inside back cover of your textbook, and now the mass is going to be just like the atomic number. It kind of follows an order. Not always, but most of the time. So, let's look for 79.90. What do we have? Who is it? Who's our mystery guest? Bromine. Yeah, bromine. And look at the mass on bromine. 79.904. And if we round it to 2 decimals, isn't that exciting how that flashes on and off? That's because it's dying. My whiteboard is dying, or my smart board. Anyway. Yeah. So what I did down here, watch this carefully, because I think that a lot of you are getting lost in the numbers here, and it's not making a lot of sense to you. So what I did was I did this all over again, and I made up my own numbers. Okay, so what did I do here? I said X79 was exactly 79 AMs. It's not, but just for fun, I want you to see how this works with simple numbers. 50% is half, isn't it? Okay, so half of all element X has a mass of 79. You're going to see we're going to come out really close. But the important thing is you're going to be able to understand what the numbers mean. And so let's go down now and look at X81 and just assume that that's 81 AMUs. It won't be exactly right, but it'll be close. And you can see the differences in the numbers here. Okay, instead of 39.5, it was actually 40. Instead of 40.5, it was actually 39.9. So close, but not exact. But the point is that 50% of the isotope, the isotope 79, 50% of it accounts for 39.5 AMUs of atom. Isotope 81 has 81 AMUs. If 50% of that are that represents 50% of all isotope 81 that's out there, that would be 40.5. And now when we add that up, that stinks. Come on. There we go. Fix that little problem and get rid of this. And so, yeah, there we go. Now, look here. 50 and 50 are 100, right?
Yeah.
100% is all. That's all of the atoms of bromine that we have in the entire world. And of that, 50% are isotope 79, 50% are 81. And if I change my 100% to a regular number, I have to move my decimal 1, 2 to the left, and that gives me 1. So 1 is the whole. Is this starting to come together for you, I hope?
Yeah.
At least some of you. Okay. And so look at the number I got here with my estimate. It's very close to what we got up here. But the more important thing is that the simpler numbers make it a little easier to follow, I think. Okay? Let's go on to the last one here, and let's get a shade up to make it easier to follow. Come on. Here we go. Okay. In this one, we have x25. Do you all understand that the 25 after the element means that's an isotope? And that that's what? What does it represent of the isotope? Come on, say it. Someone's going, what is it?
Mass.
It's the mass number. Yeah, it's the mass number. Okay, so this is the mass number, and if we were writing element X, and it had a mass number of 25, that would be it for that isotope. Now, we don't know what the bottom number is. That's what we're going to figure out. Okay, down here we have X26, and you can see, just like before, we have a 9 here to the right of the decimal, so that makes this rounded to a 25, and a 9 here rounds this 25 to a 26. Now, we were told these abundances, 10% for this guy, and 11%, 11.01% for this guy. Together, we have 2.499 AMUs when we multiply this guy out. That is 24.986 times 0.1. Move the decimal 1, 2 to the left. Now, over here, we've got 25.982 times 11.01, and these are our total mass units that are represented by these two isotopes. But there's 3 isotopes. Wait, there's more! Okay, so what are we supposed to find here anyway? We want the AMUs for X24. Well, whoa, how do we find that? What do we have to know? We got to find something else out. Ah, we got it. And here it is. Woo! Look at that, huh? Given to us right in the problem. That is the average. Ah, now we know who the element is. Let's find it. Who's our mystery guest? 24. Oh, magnesium. 24.3. See it? Magnesium, number 12. Okay, so we know that this is element number 12. There's the atomic number. Now, that's not required in this problem, but it's nice to know. Now, to finish this guy off, what we do is we say, right here, we've got the mass. Sit down. Right here we have the mass of 25 and 26. Or 27 and 26, what was it? 25 and 26. Okay? And that came out to this number right here, which goes down here. Yeah. If I add in the AMUs for the third isotope, which is what they're after, that's going to be the question. The total average was this guy. Now, this is just like algebra. A plus B is equal to C. And so we subtract 5.360 from both sides, and that will give us our answer, which I don't have written here. So I'll write that out, and you all can go. So the actual number for question mark, which is our other isotope, is that this is equal to 19.945, and that's what they were asking in this question. This, of course, is AMUs. And that's how you get that little guy. I hope these are helping. And so spend some time with them and see if you can get it all understood. Bye-bye.